morning to all of you. Hope you had a nice sleep yesterday night after a long day, and today we will start with a new topic, and the topic that we will cover in the morning session is dynamics of inviscid flows. So, what we essentially intend to cover in the dynamics of inviscid flows. So, you have learnt the differential equations which describe the statics of fluids. Now, if the fluid is in motion, there can be various forces acting on the fluid, but it is possible that out of the various forces which are acting on the fluid, the viscous forces are absent or the viscous forces are not important. For example, as a practical example, I can say that close to the solid boundary viscous effects will be very important, but if you go further away from the solid boundary, there is a region called as boundary layer beyond which viscous effects will not be important, and then you can in that region you can write the equations of fluid flow without taking viscous effects into consideration, and that many times may simplify the solution of your problem. That is the motivation of studying the dynamics of this inviscid flows. Inviscid flows means flows that do not have any significant viscous effects. So, to write equation of motion for inviscid flows, what we will do is we will start with drawing a box with which we started in many of our earlier examples. Let us say that you have a rectangular box and let us say that let us give some dimensions to the sides of this box, but before that we set up the coordinate axis x, y and z, and the dimensions along these are delta x, delta y and delta z. Now, the question is that we will write the resultant forces on this box, we will write a description of the resultant forces acting on this box. Now, what can be the resultant force for, what can be the forces for inviscid flow? So, you have to remember that in continuum mechanics there are two types of forces, one is a surface force and the other is the body force. The surface force has the normal component and the tangential component or shear component. Now, the shear component arises because of viscous effects. So, when viscous effects are not present, you will have only the normal component, and that normal component also not because of viscous effects. There we will show later on that there can be normal component of stress due to viscous effect as well, not that due to viscous effect only tangential component of stress can be there. There can be a normal component of stress also because of viscous effect, but when viscous effects are present are absent, you have the normal component of force manifested only in the form of pressure and its gradients. So, the surface force that we talk about here, that is essentially about the normal component of stress due to pressure. So, to make our life simple, we consider the forces only along x direction. So, let us consider this phase, the phase which I shade here. This phase will have force acting on it. What are the forces acting on it? So, if P is the pressure at this location, let us say P is the pressure at this location, P times delta y times delta z. Now, if you consider the opposite phase, then across the opposite face, if the pressure at the left face is P, the pressure at the right face is P plus del P del x, P plus del P del x into delta x plus higher order terms, P plus del P del x into delta x plus higher order terms. We are writing a Taylor series expansion. This times delta y into delta z. So, if you consider the other phases, they have normal directions along y and z, so they will give rise to forces along y and z. But if we are interested about forces along x only, these two are the only phases which are relevant. So, this is not a complete description of force, this is force along x only, because we are interested to write equation of motion along x. Now, along with the surface force, there will be some force which we call as body force. So, what is the body force? Body force, let us say that Bx is the body force along x per unit mass. So, Bx body force along x per unit mass. So, what is the mass of this fluid element? So, let us say that we show the body force along x in this way. So, what is the mass of this fluid element? The mass of this fluid element is density times the volume delta x, delta y, delta z times Bx is the total body force. Bx is per unit mass, if you multiply it by the mass, it becomes the total body force. So, resultant force along x, now let us write resultant force along x is equal to the mass of the fluid element times acceleration along x. So, resultant force along x, this is Newton's second law of motion, we have not written anything new for this fluid element, we have written this as the Newton's second law of motion along x. So, resultant force along x, see from the left side you have P delta y delta z, from the right side you have minus P plus del P del x into delta x plus higher order terms into delta y into delta z plus rho delta x delta y delta z into Bx, that is nothing but m x. What is m? So, m is we will write in the next sheet what is m and what is or maybe in this sheet itself let us complete before we write the simplified form. So, m is equal to rho into delta x into delta y into delta z into that into Ax. So, in the next sheet we will try to simplify this equation. So, we have a look into this equation, and what we see here is that this p into delta y into delta z gets cancelled with this p into delta y into delta z. So, what remains? If you look into this equation, you have minus del p del x into delta x into delta y into delta z. So, minus del p del x into delta y into delta z into delta x is there of course. So, into delta x plus higher order term plus rho bx into delta x delta y delta z is equal to rho ax into delta x delta y delta z. Okay. So, next what we will do is we will simplify this equation. We will simplify this equation, we will take the limit as delta x, delta y, delta z all tend to 0. So, if we do that, first of all delta x, delta y, delta z they are all tending to 0, but they are not equal to 0. So, you can cancel them from both sides, and then the higher order term will contain still some delta x, delta y or delta z in addition to this product. So, if you take the limit as delta x, delta y, delta z tends to 0, you will have this higher order term equal to 0. So, in the limit you have minus in the limit as delta x, delta y tends to delta z tends to 0. Again, why we want to take the limit as delta x, delta y, delta z tends to 0? We want to take the limit because we want to write a differential equation. Differential equation is valid at a point. So, we must shrink the volume so that the volume element delta x, delta y, delta z that shrinks to a point. In effect, that is possible if you make all the sides dimensions tending to 0. So, minus del p del x plus rho bx is equal to rho ax. So, now we have to see that how do we describe ax. See, as a teacher it is very important to follow certain sequence while you are teaching your students. Before this we studied kinematics of flows, and there we had a description of acceleration. Now we are going into dynamics where there is still a kinematic component and there is a kinetic component. The kinetic component is a force which we have described here in the left hand side, but there is a kinematic component in the right hand side which we need to describe in terms of the velocity components, and that we learned how to write acceleration in terms of the velocity components in the chapter of kinematics. So, what was it? What is Ax? Ax is nothing but del u del t plus u del u del x plus v del u del y plus w del u del z. So, to recapitulate, there are broadly two components of acceleration. One component of acceleration is this one which signifies the change in velocity at a given location due to change in time. So, that is the temporal component, and it is the advective component because of the change in position, change in velocity with respect to position, you encounter a different velocity field and that gives rise to an acceleration. So, these two effects combined together give rise to the acceleration of flow. So, this is also written as capital D dt of u, this was explained yesterday. Next what we do, we write this equation we will write this equation again by considering first the right hand side which we earlier wrote we will write in the left hand side, and whatever we wrote in the left hand side we will write in the right hand side. This is just a convention in which we commonly write the fluid mechanics equations. So, then the equation becomes rho del u del t plus u del u del x plus v del u del y plus w del u del z is equal to minus del p del x plus rho bx. Okay. So, this is the x component of the equation of motion. By analogy, let us quickly write the y component and z component. So, y component you replace u with v, so del v del t plus u del v del x plus v del v del y plus w del v del z is equal to minus del p del y plus rho by. This is y component. Similarly, z component rho del w del t plus u del w del x plus v del w del y plus w del w del z is equal to minus del p del z plus rho bz. This is z component. Now, before going into the next stage of simplification, let us emphasize that these equations of motion, I mean this we will later on see, in fact we will immediately see how to write these equations in a compact vector form, but it is the vector, it is a, these three equations are scalar components of resultant equation of motion in its vector form, which we will derive. Now, these equations of motion are known as Euler's equation of motion. Euler's equation of motion. Euler's equation of motion. So, Euler's equation of motion, what is the assumption that goes behind? Remember, whenever you are teaching some equation to your students, always emphasize on the assumptions under which that equation is valid, because all equations will not be valid for all cases. So, Euler's equation of motion is valid for inviscid flow, that is the restriction. Now what we will do is we will see that how to write this in a compact vector form, u del u del x plus v del u del y plus w del u del z. So let us do that in the next sheet of paper. So let us write the velocity vector v as ui plus vj plus wk, and the del operator I del x plus j del y plus k del z. So del of u, grad of u becomes I del u del x, j del u del y, k del u del z. So that is how you can make any operation on del. Now if you write v dot del, simply v dot del, this is an operator. So what is this? You have ui dot I del x. So u del x plus v del y, sorry, v del y plus w del z. So if you write v dot del of u, it becomes u del u del x plus v del u del y plus w del u del z. So what we can see is that we can write u del u del x plus v del u del y plus w del u del z in a compact form v dot del u. So the Euler's equation of motion x component becomes rho del u del t plus v dot del u is equal to minus del p del x plus rho bx. Similarly other components del v del t plus v dot del v is equal to minus del p del y plus rho by. Third component rho del w del t plus v dot del w is equal to minus del p del z plus rho bz. Now what we do is we will take the, we will have I of this plus j of this plus k of this. So I of this, j of this and k of this, where I is the unit vector along x, j is the unit vector along y and k is the unit vector along z. So basically we are making a vector sum by, so if you have 3 components of a vector, what you do? First component I cap plus second component j cap plus third component k cap becomes the resultant vector. So here the first component I cap plus the second component j cap plus the third component k cap. So this we add together to make a vector equation. So when we make that, see, let us do it here itself before going into a next page. So what you see here is that it is del u del t I cap plus del v del t j cap plus del w del t k cap. So del t of with rho of course is there outside, del t of u I cap plus V j cap plus W k cap, okay, plus V dot del U I cap plus V j cap plus W k cap. This is the left hand side, okay. So, what you can see from here in the left hand side, U I cap plus V j cap plus W k cap, this is the velocity vector V, and this also U I cap plus V j cap plus W k cap, that is also velocity vector V. So, before this page becomes too clumsy, we will go to the next page and complete the equation, but I will show you the previous version so that the continuity of discussion is maintained. So, if you see the left hand side, let us write the left hand side, rho del V del T plus V dot del V now look at the right hand side. Right hand side is what? Minus I del x plus j del y plus k del z of p. That means we have already discussed the del operator, which is I del x plus j del y plus k del z. So, minus I del x plus j del y and k del z, it effectively becomes minus of grad p, and the last term rho bx I plus rho byj plus rho bzk, it becomes plus rho into the vector b. What is the vector b? The vector b is the body force vector per unit mass, which is bxi plus byj plus bzk. So, this equation is a compact representation of the Euler's equation of motion in its vector form. Now, we will simplify this equation. Before simplifying, what we will do is we will describe a vector identity. So, vector identity V dot del V is equal to half del V dot V minus V cross del cross V. This is a vector identity which follows from the mathematics. If you look into any engineering mathematics book and get into the chapter of vector calculus, you will find this identity and possibly the derivation of this identity. That is beyond the scope of this course to discuss more about this identity, but here we are making use of this identity to simplify this equation. So, instead of or in place of this V dot del V, we will be writing this expression. So, we will move on to the next page. So, if we replace the del v dot del v with that identity, you will get rho del v del t plus half del v dot v minus v cross del cross v is equal to minus grad p plus rho b. Okay. Next what we do is, we want to consider a line element, small line element dl, small line element dl, which is the vector element. So, dl is dxi plus dyj plus dzk. We want to make a dot product of this with dl. So, the dot product of this equation, so the operation is we make a dot product of this equation with dl. Physically it means that we want to make a projection of this equation along a line element, and later on we may choose this line element as a part of a streamline, that we will see later on. So, what we will do is, we will take the projection. So, first term rho del v del t dot dl, it becomes rho del t of v dot dl. This is straightforward. Next term rho into half, what is del v dot v? V dot v is v square. So, del v square, del of v square dot dl. So, what is that? Rho half I del x of v square plus j del y of v square plus k del z of v square. This dotted with dl dxi plus dyj plus dzk. So, if we do that, let us see this simplification. This I component dot product will come with this I component. So, it will become, if we write this simplification here just for the sake of completeness, rho by 2 del v square del x into dx, these two dot product, del v square del x into dx plus del v square del y into dy plus del v square del z into dz. So, del x into dx plus del y into dy plus del z into dz of v square. So, that becomes d of v square. What is that? What is d? D is del x into dx plus del y into dy plus del z into dz. So, this becomes, this term becomes rho by 2 d of v square. So, rho into d of v square by 2. Let us move into a new sheet of paper. So, we have just now shown that rho into half del V square into dot with dl becomes rho by 2 into dV square. Okay. Next term we will not simplify, next term is what? Next term is V cross del cross V dot dl. What is del cross V? This is nothing but the vorticity. So, this is the vorticity omega. So, this becomes V cross omega dot dl. We will not simplify it, but keep it like this. In the right hand side the first term is minus of grad P. So, grad P dot dl, that is equal to I del P del x plus j del P del y plus k del P del z dot I dx plus j dy plus k dz. So, this becomes del P del x dx plus del P del y dy plus del P del z dz. So, this becomes dP. Last term rho B dot dl. Now, what is the body force? There could be several body forces acting on the system, but let us just assume that it is the only body force is due to gravity, and gravity acts along the negative z direction. So, this is the positive z and gravity acts along the negative z. So, B is nothing but what? Minus g k. So, B becomes minus g k, that means this becomes minus rho g k dot dxi plus dyj plus dz k. So, minus rho g dz. So, we have simplified all the terms in all the equations, and now let us combine all the terms. So, rho del T of V dot dl plus d of V square by 2, it was we derived it as half d V square. So, we are taking the half inside the d minus V cross omega dot dl is equal to minus dP minus rho g dz. So, we take the all the terms, I mean some of the terms in the left hand side and write this as dP plus rho g dz plus d of V square by 2 is equal to minus rho del T of V dot dl plus rho V cross omega dot dl. Okay. We have just rearranged the equation. Now, we will look into the cases when the right hand side of this equation becomes 0. So, when the right hand side of the equation becomes 0, so the question is, when does right hand side become equal to 0? The first case is steady flow. The first requirement is steady flow, because if it is steady flow, this term will be 0 for steady flow. The second possibility is that when V cross omega dot dl equal to 0. So, when is it 0? Let us try to investigate that physical situation. When is V cross omega dot dl equal to 0? When is V cross omega dot dl equal to 0? So, what we do? We consider certain cases. Case 1, dl along a streamline. Why dl is along a, why it is 0 when dl is along a streamline? Then the direction of V and the direction of dl will be the same. Why? Because by definition of streamline, V is tangential to the streamline, and if dl is also along the streamline, see V cross omega is a vector perpendicular to V. So, it is perpendicular to the direction of the vector V, and therefore, its dot product with dl, which is also in the direction of V, will be equal to 0. So, if dl is along a streamline, V cross omega dot dl will be equal to 0. I am repeating again, if V is along if dl is along a streamline, then the direction of V and direction of dl are the same. Then V cross omega is perpendicular to that direction, and the dot product of that direction with the perpendicular to that direction is 0, because dot product of two vectors which are perpendicular to each other, that becomes 0. So, dl, if dl is along a streamline, this will be equal to 0. Case 2, vorticity is a null vector, that the fluid has no vorticity, that is irrotational flow. So, if it is irrotational flow, then this vector omega, the vorticity vector, is a null vector, and that makes this automatically 0. So, case 1 or case 2 or case 3, any of these 3 cases will make this equal to 0. V cross omega perpendicular to dl. So, if your line element dl is such that V cross omega is perpendicular to that, then their dot product V cross omega dot product with dl will be equal to 0. So, if any of these 3 cases is possible, then you will have V cross omega dot dl equal to 0. So, we consider either of these cases plus steady flow. So that the del del t term becomes 0. So, if we do that, then only the left hand side of this equation, only the left hand side of this equation, see the right hand side for steady flow this term becomes 0, or the 3 cases which we have just now considered, if any one of them is satisfied, this term will become 0. So, the left hand side then will become 0 and we will write that equation. So, the left hand side of the equation becomes dP plus, okay, there was a rho that we missed in that equation, please correct that equation. D of, when we have written d of v square by 2, there was a rho outside. So, rho into d of v square by 2, because if you look into the previous equation it was multiplied by rho into d of v square by 2. So, the rho has to be there, please correct this equation. So, dP plus rho d v square by 2 plus rho g dz is equal to 0. This is another form of the Euler equation. Can you tell what are the assumptions under which this equation is valid? So, first and foremost, the mother of all the assumptions for Euler equation and its derivatives or its variants is that inviscid flow. Then, so let us write inviscid flow, steady flow, and any one of the 3 cases presented is satisfied or valid. What are those 3 cases? Either flow along a streamline or not flow along a streamline, your choice of the line element is along a streamline. So, that is number 1. So, you are considering the equation of motion along a streamline, that is number 1. Number 2, irrotational flow, or number 3, V cross omega perpendicular to dl. So, if out any one of these 3 cases presented is valid. So, if that is the case, then this equation is valid. So, we can divide this equation by rho and write dP by rho plus d of v square by 2 plus g dz equal to 0. Now, we need to integrate this equation. So, question is what are the points across which we can integrate. So, we integrate these two. So, when we integrate this equation, we have to keep in mind that this term rho, that is an important factor, because P itself can be a function of rho, which is true for a compressible fluid. Before coming into that, we have to discuss very critically that where will these points 1 and 2 lie. So, for that we have to consider the 3 cases that we have presented. The first case was along a streamline. So, if it is along a streamline, it does not matter whether it is irrotational flow or rotational flow or whatever. So, if we take it along, if we take the line element along a streamline, then we can integrate this equation between 2 points along the same streamline, does not matter whether the flow is irrotational or rotational. So, 1 and 2 along a streamline. If you take 1 and 2 along a streamline, then you can integrate this equation along a streamline. Let us say that we have a streamline like this, we take points 1 and 2. The other important issue that we would like to highlight is that when you have dp by rho, if that rho is a constant, it is not a function of p, we can bring this rho out of the integral. So, if it is an incompressible fluid, if the fluid is incompressible, then we can take rho out of the integral, because for incompressible fluid p is not a function of rho. So, for incompressible fluid, integral of dp by rho is equal to 1 by rho integral of dp. So, 1 to 2, this becomes p2 minus p1 by rho. So, then this integral we can write p2 minus p1 by rho plus integral d of v square by 2 becomes v square by 2. So, v2 square minus v1 square by 2 plus integral g dz, if we are considering that g is constant over the range of height considered, then we can take g out of the integral and write g into z2 minus z1, this is equal to 0. So, we can divide both sides by rho and write p1 by rho g plus v1 square by 2g, we take all the minus signs in one side and all the plus side signs in another side, plus z1 is equal to p2 by rho g plus v2 square by 2g plus z2. This is your well known Bernoulli's equation. So, we have to remember that there are many ways of presenting the Bernoulli's equation. We will discuss about the different ways of presenting the Bernoulli's equation, but before that we will try to again emphasize on what are the assumptions under which this equation is valid. Very important, whenever you teach Bernoulli's equation to your students, a couple of things that you should keep in your mind. First, the assumptions, and the second of course the physical meaning of various terms. So, first I will discuss about the assumptions behind this equation. So, you can see here that in this equation you have what we have done is we have considered that the flow that the points 1 and 2 are located along the same streamline, but even if your points 1 and 2 would have not been there along the same streamline, it would have worked provided it was irrotational flow. Remember the three cases, first is dl along a streamline, so that is the case that we have considered, but even if dl is not along a streamline, it will work that points 1 and 2 can be any 2 points in the flow field provided that the flow is irrotational. If the flow is not irrotational, then that will not be true. So, we will list down the assumptions. So, first assumption is inviscid flow. Second assumption is steady flow. Third assumption is constant density fluid or incompressible fluid. Incompressible fluid where P and rho are not dependent, and the fourth, along a streamline or if you want to generalize it, maybe between 2 points, any 2 points provided the flow is irrotational, or between any 2 points for irrotational flow. Okay. Next we will discuss about the physical meaning of this Bernoulli's equation, and then we will talk about one possible variant where the unsteady term is kept, that is known as unsteady Bernoulli's equation. Before going into that, let us discuss about the physical concept behind the Bernoulli's equation. The first term, okay, we will not start with the first term. How many? There are 3 terms. One is P by rho g, another is V square by 2g, another is Z. So let us try to give a physical interpretation to this. First, V square by 2g. V square by 2g we can write half mv square by mg. So this is what? This is nothing but the kinetic energy per unit weight. Similarly Z, what is this? mgz by mg. So this is nothing but the potential energy per unit weight. So this is kinetic energy expressed per unit weight. Remember that there is a technical term in fluid mechanics where we call as energy per unit weight as head. So this is kinetic energy head, this is potential energy head. Kinetic and potential energy all of us can understand, but what is this? Many people will call this as pressure energy, but I do not understand what is pressure energy. If you tell pressure energy, well, it is a name, I do not mind giving it a name pressure energy, but what is the physical meaning of this term? Why should you have this energy? So to understand that, let us take a simple example. Let us say that you have a pipe, and let us say that some fluid is entering the pipe and there is a pressure P. Because of the pressure P, the fluid has to do some work to maintain the flow in presence of pressure. So what is that work? Let us consider a small displacement of the fluid delta x, and let us say that A is the area of cross section of the pipe. So what is the work done? In presence of pressure, the work done in presence of pressure is the pressure times area is the force times the displacement is the work. So this is the work done in presence of pressure. So this work done is called as flow work, or the fluid has to have energy to maintain flow in presence of pressure, energy equivalent to this. So that is also called as flow energy or flow work. Expressed per unit weight, it becomes P A delta x divided by what is the weight of this fluid element, shaded element. The weight of this shaded element is A into delta x into rho into g. So, delta x and delta x get cancelled, A and A get cancelled. So, it becomes P by rho g. So, this P by rho g becomes flow energy or flow work, that is a correct technical term instead of pressure energy. So, what is flow energy or flow work? Flow energy or flow work is the energy per unit weight of the fluid that the fluid must possess to maintain flow in presence of pressure. So, now we have loosely said that the flow must possess, but flow is not possessing any energy because the flow is continuously taking place. So, what is happening here? What is happening here is something like this. Let us consider a practical example. Let us say that you have a conveyor belt in an airport and you put your suitcase. The conveyor belt is like the fluid flow and your suitcase is like the mechanical energy that you have put into the fluid flow. The suitcase will be continuously transmitted and not possessed by the conveyor belt at any position. So, some total of the energy packet that you have provided to the flow gets conserved because the conveyor belt possesses or the conveyor belt transmits, it does not possess but it transmits the suitcase from one location to the other. So, there is a conveyor belt which is transmitting the suitcase or transferring the suitcase from one place to another. Similarly, the fluid flow is transferring or transmitting a packet of energy from one point to another. This packet of energy that we are talking about here is a mechanical energy. In the mechanical energy we have three components: the kinetic energy, the potential energy and the flow energy. So, normally you have only the kinetic energy and the potential energy, but where from do you have the flow energy? Because it is a moving system, it is a flowing system, it must maintain the flow in presence of pressure. So, it must have some additional energy beyond the energy of a stagnant system. So, that additional energy that is required to maintain the flow in presence of pressure is known as pressure energy or flow energy. So, sum total of the kinetic energy, potential energy and flow energy transferred in a flow is conserved as the flow is taking place in a non-dissipative system, that is there is no viscous dissipation, there is no viscous effect. So, if there is no viscous dissipation, the mechanical energy is conserved. So, the Bernoulli's equation can also be perceived as a mechanical energy conservation equation. I believe that the physical interpretation of the Bernoulli's equation is clear to you. Now, so we have considered only steady flow, but I will try to bring your attention on one of the previous simplifications where we had considered considered the time derivative term. So, in one of the former derivations of the Euler equation, and it is in the form that we described, we had this term, the term which I have boxed is equal to 0, but what happens if it is a steady flow, unsteady flow. So, to do that we will consider that this term is still 0. So, all the out of the three assumptions, that the assumptions that we have made are valid, but let us consider this term minus rho del del t of v dot dl. Let us consider that we are considering along a streamline, but it is unsteady flow. So, along a streamline we can write v into epsilon s, where epsilon s is a unit vector along the streamline. dl is ds into epsilon s, where epsilon s is unit vector along the streamline if dl is along a streamline. So, v dot dl v dot dl is v ds. So, minus rho del del t of v dot dl is equal to minus rho del v del t ds. So, this term which was considered to be 0 in the right hand side, for unsteady flow this will no more be 0 in the right hand side. So, we had the term dp plus dp by rho plus d of v square by 2 plus g dz, which was considered to be 0. Now, in place of that we will have in the right hand side. So, if you look into this equation was the right hand side was 0, but because of the unsteady term present, now the right hand side is not 0, right hand side will become minus del v del t ds. Now, we can integrate this along a streamline. This is another version of Bernoulli's equation if you take rho out of the integral, and that we will write now. So, 1 by rho P2 minus P1 plus V2 square minus V1 square by 2 plus G into Z2 minus Z1 is equal to minus integral of del V del T ds. That means P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2 plus integral of del V del T ds. So, we have this extra term beyond the standard Bernoulli's equation. This equation is known as unsteady Bernoulli's equation. Before going into some other forms of the Bernoulli's equation, let us quickly work out a problem to illustrate some of the concepts that we have learnt so far today. Example, we will go to our example that we considered yesterday for one of the problems in kinematics. Let us say you have a 2-dimensional velocity field, u is equal to ax and v is equal to minus ay. Calculate the pressure difference between 2 points in this flow field P2 minus P1. So, there are two alternative ways of working out this problem. One is you write the Euler's equation in terms of its x component, y component and z component, find out the pressure gradients along x, find out the pressure gradient along y and the pressure gradient along z, and find out the total change. Now let us try to investigate here whether Bernoulli's equation is applicable or not. So let us make certain assumptions. So first assumption is that this A, capital A is not a function of time. If capital A is not a function of time, it is steady flow. Whether it is irrotational flow or not, let us check. So we will consider that it is inviscid flow, that is an assumption, and why we are making the inviscid flow as an assumption I will discuss in a moment, but before that let us check whether it is irrotational flow or not. So what is the angular velocity or what is the vorticity component with respect to z axis, that is del v del x minus del u del y, that is the only vorticity component. Del v del x is 0 and del u del y is 0 for this velocity component. So that makes this equal to 0. So this is irrotational flow. Because it is inviscid flow and irrotational flow will remain irrotational. I will discuss about this in a moment after solving this problem. So when you have inviscid flow, so what are the assumptions that we have which are valid here? Steady flow, inviscid flow, incompressible fluid we are assuming, and irrotational flow is justified from the given velocity profile. That means you can apply Bernoulli's equation not just along a streamline, but because it is irrotational flow you can apply it between any 2 points 1 and 2. So you can write P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. So P2 minus, so let us write, let us look into this equation again. So P2 minus P1 by rho is equal to V1 square minus V2 square by 2 plus G Z1 minus Z2. Assuming that Z1 equal to Z2, this we are making an assumption, then P2 minus P1, which is the question that is asked, is equal to rho into V1 square minus V2 square by 2. What is V? V is square root of u square plus V square. So this is a square root of x square plus y square, because u is ax and v is minus ay. So v square is a square into x square plus y square. So P2 minus P1 is equal to rho by 2 into a square into x1 square minus x2 square plus a square into y1 square minus y2 square. Okay. So you can see that we can apply Bernoulli's equation for this problem, but we have to test and we have to make certain assumptions based on which we can apply the equation. So you cannot just blindly apply the Bernoulli's equation. So we can see that one of the important considerations for which based on which we can apply the Bernoulli's equation between any two points is that the flow is irrotational. But even if the flow is irrotational, it may not remain irrotational forever. So let us quickly see that what are the factors that can make an irrotational flow to a that can make an irrotational flow a rotational flow. First is presence of solid boundary. So if you have a solid boundary, what it tries to do, it tries to arrest the velocity and therefore it creates a velocity gradient, and because it creates a cross velocity gradient, it creates a rotationality in the flow. So even if the flow was originally rotational, because of the presence of the wall, because of the presence of the solid boundary, because of viscous effect associated with that, the flow tends to become a rotational one. Then presence of shock wave. If you have a shock wave represents a discontinuity in a compressible flow field. So across the front of a shock wave there are strong discontinuities of fluid properties, and that can make an irrotational flow a rotational one. Thermal stratification. So if you have thermal stratification, that means you have based on density different layers of fluids are stratified. So the lighter fluid is at the top and the heavier fluids are at the bottom, and the lighter and heavier fluids are based on higher or lower temperatures. So this is called as thermal stratification, that can also make an irrotational flow a rotational flow. Then Coriolis force. What is Coriolis force? If there is a platform that is rotating and if there is something which is translating with respect to that rotating platform, then it experiences a force, that is called as Coriolis force. That force is experienced in that rotational reference frame. So for example, earth is rotating, so if there is a river or there is a ocean current which is translating with respect to earth, it will experience in the reference frame of the earth, it will experience a Coriolis force, so that it tries to get bent in certain direction. So in presence of that Coriolis force, an irrotational flow can become a rotational one. So we have to ascertain that the flow is originally rotational and these effects are not important. If these effects are important, then even an originally rotational flow will become rotational one. So flow which is irrotational forever is something what is a very interesting flow. So a flow which is irrotational forever is originally an irrotational flow, and in addition it is an inviscid flow. If it is an inviscid flow, an irrotational flow for many practical situations will remain irrotational flow forever. So inviscid plus irrotational flow is a flow which can remain for many practical purposes where other effects are not there. For many practical purposes that flow will remain as irrotational, and that kind of flow will have a velocity potential, and that is a flow which is called as potential flow, and Professor Ghosh Maulik will discuss in details about potential flows in one of our later chapters. The final item that I will discuss before bringing this session to a closure is the application of Bernoulli's equation or the derivation of Bernoulli's equation in a streamwise coordinate system, or Euler's equation in a streamwise coordinate system, streamwise and cross streamwise system. Euler's equation in streamwise and cross streamwise coordinate system. So, let us say that this S is a streamwise coordinate system. So, let us take a fluid element coaxial with the streamwise coordinate system. Let us say that this fluid element is having a length of delta S and the normal direction length is delta n. Let us say that these two faces are at a distance delta z, vertical distance delta z apart. So, if we construct a triangle like this angle theta, the sine of this angle theta is defined as delta z by delta s. Now, what are the forces acting on this element? So, here the pressure is P times the area delta n into the normal direction, let us say the length perpendicular to the plane of the figure is 1. So, rho P is P into delta n. Here in place of P it is P plus del P del S into delta S, higher order terms we are not writing, that times delta n, and you have the body force due to gravity. So, rho g will be vertically downwards, it will have its own component along S. So, let us write the equation of motion, again the Newton's second law. Resultant force along S is equal to mass of the fluid element times acceleration along x. What is the resultant force along S? P into delta n minus P plus del P del S into delta S times delta n minus rho g sin theta. This angle to be specific, this is 90 degree minus theta. So, its component along S is along the negative S direction, which is minus rho g sin theta. This is the this is per unit volume, and what is the volume of the element? That into delta S into delta n. So, m is rho into delta S into delta n, m into g is the weight, that into sin theta. So, that is why this delta S delta n is multiplied. Rho into delta S into delta n is m, and that into g is mg, which is weight, and that multiplied by sin theta. So, this is equal to m into as. What is m? Again rho into delta S into delta n into as. Now, from the right angle triangle that we have drawn here, we can see that sin theta is equal to delta z by delta S. This is the first observation. The second observation is that this P gets cancelled. So, what we are left with? We are left with minus del P del S minus rho g del z delta z by delta s, this is equal to rho a s, because delta s into delta n gets cancelled from both sides. Now you take the limit as delta s, limit as delta s and delta n tend to 0. If you take the limit as delta s and delta n tends to 0, then the higher order terms will go away, plus the higher order terms which were there, they will go away. That is the first observation. And the second observation is that delta z by delta s will become del z del s. So we can write this equation, we will write in a fresh page, minus del p del s minus rho g del z del s equal to rho a s. This is in the s direction. If we consider the n direction, so what is the n direction? If this direction is s, orthogonal to that is the n direction. Same type of force balance you can apply in this figure. We have shown force balance along s, but we can show force balance along n. So we can write minus del p del n minus rho g del z del n is equal to rho a n. So we will try to apply this equation for a very simple problem to illustrate the concept. So this is again like the Euler's equation, but written in streamwise and cross streamwise coordinate. So Euler's equation in streamwise and cross streamwise coordinate. Let us work out a problem and then we will come to a closer to this session. So let us say that you have a pipe bend. Pipe bends are very important in industrial applications. Let us say you have a pipe bend, and so in industry, so what is physically there to create a pipe bend is there is something called as an elbow. So the elbow may have different elbow angle and that can connect or join two straight sections of the pipe to form a bend. So let us say that across an elbow there are 2 points 1 and 2, and it is important that we find out what is the pressure difference between these 2 points 1 and 2. So if the bend is a circular bend, then the cross streamwise direction is as good as the radial direction. So the streamwise direction is this direction s, and cross streamwise direction n is nothing but equivalent to the radial direction. Now we cannot straight away apply Bernoulli's equation between the points 1 and 2 or Euler's equation between the points 1 and 2 if we are not considering that 1 and 2 points are located on the same streamline. Here you can clearly see that the streamlines are not the line joining 1 and 2 is not a streamline. The line joining 1 and 2 is not a streamline. Streamlines will be approximately oriented in the direction of the dotted line that is there. In fact, the line joining 1 and 2 is somewhat orthogonal to that dotted line. So we cannot straight away use the Bernoulli's equation or Euler's equation along a streamline. So what we can do, what can save us is if we check whether it is an irrotational flow or not. Very commonly flow across a pipe bend can be approximated as a free vortex flow, V theta is equal to C by R. If V theta is equal to C by R, so what is a vortex flow? A vortex flow will have only theta component or cross radial component, it does not have a radial component. So V theta equal to C by R and VR equal to 0. Let us approximate the velocity field like this. It can be shown that this is an irrotational flow. Because it is an irrotational flow, we can use the equation, the Bernoulli's equation between any 2 points 1 and 2, no matter whether they are located along the same streamline or not, provided the other assumptions, that is inviscid flow, we assume that this flow is inviscid just for simplicity, and incompressible fluid, steady flow, all those are valid. If that is true, then we can write P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Let us assume that there is negligible change in height between the points 1 and 2. So these terms get cancelled out. So P2 minus P1 is equal to half rho V1 square minus V2 square. Now because V theta is the only component, so half rho V1 square is C square by R1 square minus V2 square is C square by R2 square. So half rho C square into 1 by R1 square minus 1 by R2 square. So this is one way of solving the problem. Let us consider a method 2 where we use the Euler's equation in the cross streamwise coordinate. By that what equation we mean? By that we mean this equation. So in this equation we are not considering this effect of height term. So minus del P del N is equal to rho A n. In place of del P del N we can write del P del R for a system where the radial coordinate is same as the cross streamwise coordinate. So here because we consider that the bend is a part of a circle, the cross streamwise coordinate is same as the radial coordinate. So in place of del P del N we call del P del R, and A n is nothing but minus V square by R. This is nothing but the centripetal acceleration, and V here is only V theta, there is no other component. So del P del R is equal to rho V theta square by R. So if you integrate this now, before that we substitute V theta, so V theta is C by R, so C square by R square into R. So you have dP is equal to rho C square R to the power minus 3 dr integral of that. So pressure difference between points 1 and 2 is given by integral of R to the power rho C square integral of R to the power minus 3 dr between the points 1 and 2, and you will see that this integral will give the same result as the previous one which we derived by using the Bernoulli's equation. So this shows different ways of solving the same problem, and most importantly the assumptions that we make for solving the problem. So to summarize this session, what we have learnt? We have learnt how to write the Euler's equation of motion, how to describe the Euler's equation of motion in various coordinate systems, and how to derive the Bernoulli's equation from the Euler's equation of motion, what are the various assumptions that go behind the Bernoulli's equation, and we have illustrated a couple of examples to demonstrate the use of the Bernoulli's equation under restricted assumptions.